Uh, Hi, this is the second part of the Wednesday lecture this week, and I will talk about the definitions that are pertinent to the discussion. So the first definition is that of a Cauchy sequence. So we call a sequence Xn Cauchy if for every epsilon there exists an n, such that eventually the points get very close to each other. Convergence would mean close to the limit, but this is emphasizing close to each other. And as discussed, series are a good example of things where you get Cauchy sequences. There are other cases where you as well do, but those other cases are usually easier to analyze. Now, if you have fixed an epsilon, and you choose n bigger than, say, log 2, 1 over epsilon, and if n and m are bigger than n, and without loss of generality, we can always make n bigger than m. This is a small remark here, and the reason for that is that we have symmetry in our condition. So with that, especially with series, it's nice to make n bigger than m because the difference in Sn and Sm you can easily estimate by a difference from a sum from m plus 1 to n. And while this you can estimate from above by a sum to infinity, just to make the computation a little bit easier. And then this sum is a sum of a geometric series, so you get 1 over 2 to the m as the answer. Well, which is less than epsilon, because this is actually less than 1 over 2 to the n, and by the choice of n being quite large, this is less than epsilon. Okay, so this gives series are a common example of where you get absolute Cauchy sequences, and you also get those in Rn. We won't see this lecture yet, but in other lectures and homework. So now, second definition, completeness. We saw examples that Cauchy sequences do not need to converge, and therefore we define a space as complete, and this is analogous to the completeness properties of the real numbers. If every Cauchy sequence Xn, there exists a limit such that you converge. So, in other words, Cauchy sequences converge is the short way of defining completeness. Okay, so let's see examples of complete spaces. If we take R with the usual metric, then as we recalled, there's a theorem in 131a that says that Cauchy sequences converge. Done. Another less trivial example is any space X with the discrete metric. These spaces are also complete. So as proof, let's take a Cauchy sequence in X. This is always how, to prove that Cauchy sequences converge, we'd start from an arbitrary Cauchy sequence. Then, well, we use the Cauchy sequence property. If we use epsilon equals 1/2, so this is true for all epsilon, in particular epsilon equals 1/2, there exists an n such that far out in the sequence, after the index capital N, the points are within distance 1/2. But if the points are within distance 1/2, and because this is the discrete metric, our only options are 1 and 0, so the distance actually has to be equal to 0. But that means that these points are the same. Indeed, for every n bigger than n, and if we use m equal to n, capital N, then we get that xn is equal to x capital N, and we call this x. So if we call this fixed value x, then distance xn to x is equal to 0 for all n bigger than or equal to capital N. And this is just the same thing as saying that the limit of the distances is 0, or that xn converges to x. This is indeed related to the last lemma mentioned in the introduction to this lecture. So we get that Cauchy sequences converge in summary. Q, on the other hand, would not be an example. Not complete. Because, say, you could take an xn Cauchy and converging to pi, but this would not be in This is not quite a full proof, but it's the intuition behind it. Okay, so this is about Cauchy. The first two definitions were about Cauchy sequences, and the final definition is about compactness. It's about finding convergent subsequences. We saw examples where you cannot find convergent subsequences, unbounded spaces, or not closed subsets of R, or finally this weird discrete metric space. So to avoid these examples, we introduce a definition. We say that a metric space is compact, or we say that a subset of it is compact if every sequence of points xn in X or in K, depending on if you're working in a subset or the full space, has a convergent subsequence. Okay, so let's use again, and the idea here mainly is that we will reduce properties to 131A. So if we take a bounded interval AB, then AB is compact. And the reason for this is that if you take a sequence of points in I, well, it's points in AB, so Xn is bounded. And because it is bounded, it has a convergent subsequence. Now, by Bolzano and Weierstrass. And the limit is in I because I is in a closed interval. So we're done. So there exists a convergent subsequence that converges to something in your subset. And we should say has a convergent subsequence and the limit is in X. Well, if it's always automatically in X if the limit exists because that's the full metric space, but it has to be K. We need K, sequence K. And if we take the discrete metric, then as discussed, then it's not compact. Because say the sequence xn equals 1 over n has no convergent subsequence. One remark, for a subset of X to be compact, K must be closed. Well, proof of this, if you have xn in K and limit n goes to infinity, xn is equal to x, which belongs to x. Well, we want to show that X is also in the subset K. By compactness, there exists a subsequence X and K such that limit K goes to infinity, X and K is equal to Y for some Y in K, but Y must equal X. This part would require a more detailed proof. This is left for now as an exercise. So this proof is not quite complete, but the idea is that Y must equal X. So X, which is equal to Y, belongs into K, and this is what we wanted to show. The idea is that, well, any subsequence or convergent sequence converges to the same value X. But this requires a small proof. It's a good exercise on subsequences. Okay. So this part about the definitions, I want to conclude with an important theorem, a basic theorem. If you have a sequence of points in X, and if that sequence converges to X, then Xn is Cauchy. So one of these directions always holds. Not every Cauchy sequence has to converge, but every convergence sequence has to be Cauchy. And the proof of this is represented by a nice picture that we have this sequence of points, these black dots here, that are converging to a limit value x. And well, what that means is that they accumulate, or they get very close to x, so within some very small distance. And here I've chosen epsilon over 2, anticipating some facts from the proof. But because these points get very close to x, they also have to get very close to each other. Namely, the distance can be bounded by going via x. And this indicates a big part of the proof. Now, this class is all about writing proofs more carefully, so here I've indicated the main steps of the proof. First, we have a setup, and where we use the assumption. Then, because this is proving that Cauchy sequence or some kind of continuity property, we have to choose something, so choosing an n. And then we have to prove that our choice works. So these are 3 steps in this proof. So often there is this setup phase. And in this case, the setup phase is that we are proving that if this is true, then xn is Cauchy. So let's take something that satisfies the assumptions. So suppose I have a sequence such that it converges to x. So this is stating our assumption. And in this form, the assumption is not so useful for us. And in anticipating the fact that we will be proving Cauchy, we will fix an epsilon. And then, since limit n goes to infinity, xn is equal to x, we have that there exists an n1. And I put an n1 there because I want to differentiate it from the n in the Cauchy sequence, even though it will end up being the same. Sometimes we will need multiple ones, so it's good to have a different letter. So there exists a natural number such that after that index, every element is within epsilon over 2 from x. This is by convergence. And why I put epsilon over 2, well, we will soon see why. You don't have to do that. You could put an epsilon there. You just later notice that it's not quite good enough bound, so you quickly end up working it. Okay, well, we have to choose an n, and this is done after some scratch work, really. But our choice of n is here. I've already done this scratch work in advance, so I will choose n equals capital N1. And then I have to show that it works, meaning that if I take indices, so I let indices be bigger than m, and I want to show that the distance between x and m is less than epsilon. Well, why does it follow? Well, by our choice n equals n1, we have the n is bigger than n, and m is bigger than n, which is equal to n1. We have that, on the one hand, distance xn to x is less than or equal to epsilon over 2. And on the other hand, distance xm to x is less than epsilon over 2. So here we used by 1, what we just stated here. So if you were to write this as an answer, it would be best practice to indicate always what property you're using so that the reader doesn't have to guess what property you're using. So here I'm indicating it in audio and in words, but in a proper exam and homework answer, you would indicate that in writing. So now we combine these 2 facts that we get and use the triangle inequality to estimate the distance from xn to m is at most the distance from xn to x and from xn to x added to each other, but both of them are less than epsilon over 2, so their sum is less than epsilon. So this follows immediately from the one before. And this is what we wanted to show. So we found a capital N such that if n and n is greater than m is bigger than or equal to n, then distance xn xm is at most epsilon. So, and we did this for every epsilon positive. So by definition, Xn is Cauchy. So I think, yeah, it's good practice to add such a summarizing statement at the end of your proof. This helps the reader know exactly what you have proven and how to look at what you have proven. So it's usually just one sentence. It basically repeats what you just did, but it concludes a proof and makes for much easier reading. You will find that sometimes proofs are a little repetitive. So you'll find yourself saying the same thing a few times. Uh, at this stage, at this basic level of doing real analysis, this repetition is not hurtful. As long as you say more things than too many things than too few things, you'll be always on the safe side. Okay, so this concludes this lecture on the definitions. The next lecture will be on the some main theorems concerning compactness, completeness, and presenting their proofs.